Okay, good morning Year 12 Extension 2 students. We're going to look at some further mathematical induction questions and we'll be seeing you back at school on Monday. So let's have a look at our first question. We're going to prove by mathematical induction that 2 to the n is bigger than n squared when n is an element of the natural numbers and n is bigger than or equal to 5. Now this is an example where n is not starting at 1. Right? Most of your induction questions n starts at 1. Here, the first case is 5, and then we've got to prove it true for all the other cases after 5. So we'll start off by saying, let Pn be the proposition that 2 to the n greater than n squared, where n is an element of the natural numbers, and n is bigger than or equal to 5. Now this notation is not necessary, but it doesn't hurt to be familiar with another way of setting it out. You could just start off by saying, let n equals 5. The advantage of this notation is we can start off by saying, consider of 5. Okay, so let's look at the left hand side first for p of 5. That'll be 2 to the 5, which equals 32. The right hand side is equal to 5 squared, which equals 25. Left hand side greater than right hand side, therefore true for p of 5. Okay, next step, we'll do our assumption, right? Suppose p k is true, alright? So therefore, assume that 2 to the k is bigger than k squared, where k is an element of the natural numbers and k bigger than or equal to 5. Okay. Now, we've got to then prove true for n equals, or for p, k plus 1. Pk plus 1 there. So therefore, required to prove that 2 to the k plus 1 is greater than k plus 1 squared. Now, it will be helpful to be aware that you could also consider that as k squared plus 2k plus 1. Okay, that might be helpful later in the question. So we'll start off with the left hand side. Left hand side is equal to 2 times by 2 to the k. Okay, now look at our assumption here. Here it is. We can say, therefore, 2 times 2 to the k is greater than 2 multiplied by, now this is our assumption here, 2 to the k is bigger than k squared. Okay, so from assumption, okay, it's from the assumption. Okay, now let's think about this. 2k squared can be split up into k squared plus k squared. Okay? Now, therefore I can say k squared plus k squared is greater than. Now, let's think about this. We need to get a 2k plus 1 into the question. Alright, we've already got a k squared there, no problem. There's I'm going to use this one here. And what we're going to write down there is this is greater than k squared plus 2k plus 1. By putting that in there, it allows me to get to the k plus 1 squared. Now, we should say, since this is only true for k greater than or equal to 5, alright? If you drew a rough sketch of k squared or x squared there. Whoops, missed that one. Try again. I'll do it up here a bit bigger. So there's your parabola, and then here's your straight line. That goes through 1. So that'll be, so y equals 2x plus 1, and this is y equals x squared. Okay, so you can see here that above this value, the parabola x squared will be bigger than 2x plus 1. Now, if you look at this from a table of values perspective, do it 3 rows. K squared 2k plus 1. If I just look at some values here, 6 and 7. Alright, so k squared is 25, 2k plus 1 is 11. K squared is 36, 2k plus 1 is 13. K squared is 49, and 2k plus 1 is 15. So you can see here that k squared, definitely for values 5 and bigger, k squared is going to be bigger than 2k plus 1. So the k squared is bigger than the 2k plus 1 for k bigger than or equal to 5. So this statement here is essential because k squared is not bigger than 2k plus 1 for all values, as you can see from the graph up here. Alright? So, but that is true for values of 5 and bigger. Okay? So, and you could work that one out there if you wanted to work out the what that value is. It's definitely less than 5. So we can make that statement categorically as long as we say k bigger than or equal to 5. Okay. So, therefore, what we can say is we've got 2 to the k plus 1 is bigger than k plus 1 squared, which is what we had to prove here. Right, and then you write your conclusion. Therefore, true for n equals k plus 1 if true for n equals k, since true for n equals 5, Pn is true for all n where n is an element of the natural numbers. Okay, done. Right, we'll look at the second example in a minute.